My name is Nur Fatimah and my matrix number is 227643. I am from group 7 and I'll be start presenting the introduction and history for our assignment, which is ordinary differential equation of Newton's second law and Archimedes principle. For the introduction, Newton's second law of motion is one of the three fundamental laws formulated by Sir Isaac Newton. It describes how the velocity of an object changes when a force is applied to it. The second law provides the quantitative relationship between force, mass, and acceleration, laying the groundwork for analyzing everything from the motion of everyday objects to the trajectories of spacecraft. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The direction of the acceleration is in the direction of the applied net force. Newton's second law is crucial because it explains how forces cause changes in motion. This let us predict and understand the behavior of objects under different forces. It underpins much of classical mechanics and is applied across numerous fields including engineering, physics, and technology. Scientists and engineers apply this law in designing vehicles, analyzing structural forces, and predicting the motion of celestial bodies. During a rocket launch, Newton's second law helps calculate the force produced by the engines required to accelerate the rocket's mass against Earth's gravitational pull. Next, for the Archimedes principle, it is a cornerstone of fluid mechanics, states that an object immersed in a fluid experiences an upward buoyant force equal to the weight of the fluid displaced by the object. This principle explains why objects float or sink in fluids, with floating occurring when the buoyant force exceeds the object's weight and sinking when it doesn't. It's fundamental in understanding buoyancy, flotation, and the behavior of objects in fluids, with application in engineering, physics, and marine science. It forms the basis for designing ships, aircraft, and other structures that interact with fluids. Now, let's move on to the history part. So for the first one is the Newton's second law, where Sir Isaac Newton developed the theories of gravitational in 1666 when he was only 20 years old. Isaac Newton formulated the second law of motion as part of his work in the late 17th century, published in Philosophiae Naturalis Principia Mathematica. Newton's goal was providing a mathematical explanation for the motion of objects and celestial bodies, building on early works by scientists such as Galileo and Kepler. While Galileo had studied the acceleration of objects and the forces acting upon them, Newton formalized this relationship into a precise law. Newton's second law was revolutionary because it provided a framework that explained not only everyday terrestrial motion but also the motion of planets, moons, and comets. By defining force as the product of mass and acceleration, Newton introduced a quantitative way to link the concept of force and motion, laying the foundation for classical physics. Next, for the Archimedes principle, Archimedes was born in 287 before Common Era in Syracuse. With a strong early interest in science, he studied at the famous school of Alexandria. He made major contributions to the mathematics and physics, including the method of exhaustion, which is used to calculate areas under curve, and a highly accurate estimate of pi using regular polygons. One of his most famous discoveries is explained in his work on floating bodies. This led to what we now call Archimedes' principle, which states that an object fully or partially submerged in a fluid experiences an upward, which is buoyant, force equal to the weight of the fluid it displaces. This principle is fundamental in understanding buoyancy and fluid mechanics.
Hello, my name is Ashri Chanshari Musliman. My matrix number is 230083, and I will continue with the principle of Newton's second law and the Archimedes principle. As you can see in this slide, the general equation for Newton's second law is F equal to ma. I have researched, we can relate it with the momentum equation, which is the P equal to mv that can be derived to dp over dt and equal to m dv over dt. We can relate it with the equation of force that can be seen as F equal to m dv over dt. We can do further derivation result for the F, which is the F equal to m d square y over dt square. And finally, we can get the second order of ODE or ordinary differential equation, which is the d square y over dt square equal to F over m. We move to Archimedes principle. The general equation of buoyant force or the upward force for Archimedes principle is rho GV. The breakdown for this equation is that an object will continue to sink until the weight of the fluid displaced is equal to its upward force. We can see here the equation is upward force of water on a barrel, for example, equal to the weight or the volume of fluid displaced. In the question, sometimes they're not giving the density of rho of the fluid. If they're not given the rho, we can search it using the rho equal to m over v formula. As you can see here, uh, that one is not p. It is called a Greek symbol called rho, which is the density of fluid, and v is volume of displaced fluid. We move to application of Newton's second law and Archimedes principle. The first one I will tell the Archimedes focus part, which is the naval cargo. As you can see, the general equation is Fb buoyant force equal to rho gv, and we can relate it with the Newton's second law, which is we get earlier F equal to m d square y over dt square. We can relate the two equations to get this equation, which is the rho gv equal to m d square y over dt square. Then we move it, and we get the second order differential, second order of ODE of Archimedes principle, which is the d square y over dt square equal to rho gv over m. We move to the second application for Newton's second law focus part. As you can see, there is not much different with the first application, which is the naval cargo. For the offshore area, you can see the derives Newton's second law, the F equal to m d square y over dt square, and we just move it, and then we get the second order ODE for this offshore area, which is the d square y over dt square equal to F over m. Then I move to Amalia's part, which is the example.
Hi, my name is Amalia and I'll be talking about the examples. So the first example is a cylindrical barrel S meter in diameter of weight W Newton is floating in water as shown in part A. So after an initial depression, the barrel exhibits an up and down bobbing motion along a vertical line, which is the y-axis. So using part B, determine a differential equation for the vertical displacement if the origin is taken to be on the vertical axis at the surface of the water when the barrel is at rest. So use Archimedes principle, or upward force of the water on the barrel is equal to the weight of the water displaced. So you can read the other information. So we're going to use it for the solution. So this is the solution for question 1. So first we need to find the volume of displaced water. So for this particular one, we use the volume of cylindrical because we're using a cylindrical barrel. So V equals to pi r square h. So the r is given as over 2 and the h as y. So we got the volume of displaced water is pi over 4 s square y. And then we're going to use Archimedes principle, which is Fb equals to density of water GV. So upward force of water on barrel equals to weight of water displaced. This is the information given. So we're going to combine this volume and Archimedes principle, and then we'll get 1000 pi over 4 s square y, and then simplify this and we got 250 pi s square y. And then we can find the Newton's second law, which is F equals to ma. So here W over G is actually the mass because W equals to mg, so M equals to W over G. And then the d square y over dt square is the acceleration, and then just put in that what we found before, which is 250 pi s square y. So we rearrange this formula, and then we got the d square y over dt square is equals to 250 pi s square yg over w. So this is actually the second order ordinary differential equation. So that's all for this question. Next is example 2. A cylindrical buoy with radius r and mass m floats vertically in water of density rho w. When it is slightly depressed and released, it oscillates up and down. Derive the differential equation that describes its vertical motion yt where y equals to 0 is the equilibrium position, and assume downward displacement is positive. Neglect any damping forces. So the solution for this question is, first, we need to do the forces acting on the buoy, which is there's weight and also buoyant force. So at equilibrium, y equals to 0, we h be the submerged depth of the buoy. So the volume of displaced water is the same as the first question because we're using also cylindrical. So v equals to pi r square h. So then the Archimedes principle, which is Fb equals to density of water gv. So we got rho w g pi r square h. Just put in the volume that we got, and then at equilibrium the net force is 0. So the weight minus the buoyant force is equals to 0, and then leave w alone. W is mg, and then Fb, make it to the right side, we got rho w g pi r square h, and then we're going to leave m alone, and then we got this rho w pi r square h as equation 1. So when displaced yt, the new submerged depth is h plus y. So when we change the height, the new volume will be changed too. So the new volume of displaced water is v equals to g pi r square h plus y, and the buoyant force is Fb equals to rho w g pi r square h plus y. Next, using Newton's second law, F net equals to W minus Fb. So F net is equals to ma, right? So here a is d square y over dt square. And then just take the equation from before. So m d square y over dt square equals to mg minus rho wg pi r square h plus y. And then we can expand this equation, and then we got m d square y over dt square equals to mg minus rho wg pi r square h plus rho wg pi r square y. So from equation 1 that we got before, the first two terms on the right hand side cancel out. So we're left with m d square y over dt square equals to negative rho wg pi r square y. And then rearrange to get the d square y over dt square, we got negative rho w g pi r square y over m. So this one is also the second order ordinary differential equation, just like example 1. So that's all for the examples.
For the conclusion for this project, we can say as the group member in this report, the group member are directly exposed to the knowledge of advanced mathematics based on the Newton's second law and the Archimedes principle. From introduction, history, working principle, application to the example of both law and principle, we are directly exposed to it. Each member is advised or required to research the relation between the ordinary differential equation and Newton's second law along with the Archimedes principle. In conclusion, we as a group member can say that physics and mathematics are the two things that will not leave each other, especially if it is about derivation and integration. That's all from me. Thank you.
That's all from us. Thank you.